Hello, we are going to see now an example of modeling and optimization. As we saw last class, optimization is nothing but finding the maximum and the minimum values of a function. In this example, we are given 2700 square centimeters are available to make a box with a square base and a top. And we are asked to find the largest possible volume of the box. So, as we saw last class, our first step to solve this kind of problems is to identify clearly the givens and, if possible, draw a diagram to help us visualize the problem. If we draw a little diagram here, we are dealing with a square base box. Let's top, then we would be able to see this bit. So that's our box. We can identify elements in our box, and we can say that if this is, we call this side X, then because it's a square base box, this would be X. We don't know the height, we can call it Y. So we have a diagram to help us visualize the problem. Now let's see the givens. We have an area, total area available of 2700 square centimeters. So the area of the box would be at the most 2700 square centimeters. The total surface area would equal 2700. Now we know that the total surface area for this box would be the area of the base plus the 4 sides. We won't include the top because we know that it's an open top. So that should equal 2700. The area of the base, if we have called the side X, the area of the base would be X squared, and the area of 4 sides would be 4 times the area of one side. And if we look at one side, the area of this side would equal X times Y. And that would equal 2700. Our second step would be to identify the quantity that we want to optimize. In this case, we want to find the largest possible volume. So we want to maximize volume. The quantity to optimize is the volume. The third step is to express the quantity that we want to maximize. Let's call it volume B. In terms of the variables that we have defined. So in this case, the volume would be area of the base times height. Don't worry if you don't remember all the formulas for areas and volumes for this kind of problems. You are going to be given the formulas in any test or quiz. The area of the base in this case would be X times X, X squared, and the height would be Y. There we are. We have the quantity that we want to optimize, in this case maximize, in terms of the variables that we defined at the beginning. The next step is to express this quantity in terms of only one variable. And for that, what we do is look back into the givens and see how these variables relate. We can solve in this expression, we can solve for y. If we solve for y, what we obtain is 2700 minus x squared, everything divided by 4x. And then our fourth step in solving these problems is to express the quantity that we want to optimize in terms of only one variable. V would equal x squared times y, but y is all this expression, so we copy all the expression, 2700 minus x squared divided by 4x. Okay? And before we move ahead, we always will have a look at the expression that we obtain in terms of only one variable, and we try to simplify to the minimum expression. The first thing we notice is that we have x squared times this fraction. We can simplify this x squared with the x in the denominator. We can then express the volume here by foiling, and it would be 27x, we're distributing the x times x squared would be x cubed, everything over 4. We can simplify even more by dividing this first term by 4 and then the second term by 4. Let's do that. 2700 x divided by 4 minus 1/4, we can leave it like that, x cubed. This is 675x minus 1/4 x cubed. Now we have the quantity that we want to optimize in terms of only one variable. The fifth and last step is to maximize or minimize the expression, depends on what they are asking for. In this case, the largest possible volume would be to maximize the function volume. And to maximize and minimize, what we do is find first our CPs. Remember the critical points. Why the critical points? Because it's at those points where our function will have its maximum and minimum value. To find the critical points, we differentiate our expression. This would be, the derivative would be 675 minus, we roll down the 3, multiply 1/4, 3/4, x squared. And we equal our derivative to 0. 675 would equal 3/4 of x squared, and x squared would equal 675 times 4, everything divided by 3. This is 900. If that is 900, then we know that x would equal plus minus root of 900, and x equals 30. That means at that value we will have our maximum volume. But we know that the volume of our box depends on x and y. So what we need to do now is find the value of y for x equals 30. Where do we go to do that? To the expression that relates x and y, this expression. So y, when x equals 30, y would equal 2700 minus 30 squared, everything divided by 4 times 30. If we operate carefully, we obtain that y equals 15. There we are, we have x and we have y. We have found the values that would maximize our volume. Therefore, our volume, the maximum volume that we are going to call it Vmax, that we can find would be x squared 30 squared times y times 15. And this gives us a maximum value of 13,500 cubic centimeters. Mind the units, we are dealing with volume, cubic centimeters, and that would be our final answer. Now, recapping what were the steps that we follow to solve this kind of problems. First step, make sure that you are clear about the givens. Draw a little diagram if necessary to visualize the problem. Second step, identify what is the quantity that you want to optimize. In this case, it's the volume, and we maximize it. Third step, express that quantity in terms of the variables that you have defined. Fourth step, express that quantity in terms of only one variable. Once you have it in a simple expression, the fifth and last step is maximize or minimize the function by finding the critical points. You obtain the value of x and y that maximize or minimize your function, and then you find that maximum or minimum value. And that's it for today. Bye bye.